objects that are in free fall are still considered to have a constant acceleration, okay? And so if we have a constant acceleration, that means we can use our kinematics equations. But however, the acceleration is not due to something pushing or pulling it. The acceleration that we experience is due to gravity, okay? It's due to gravity. So I want you to think about this question. Do objects that are heavier, do they have a greater mass, do they fall faster than objects that are lighter? Right? Assuming that they're the same shape. What do we think? Okay? Some of you say yes, some of you don't know, but the answer is no, right? Heavier objects do not fall faster than lighter objects. It all has to do with air resistance. So if we can ignore air resistance, then we've got objects that fall at the same rate. And so we're going to watch a little video here. It's kind of a funny, funny video about how this was kind of brought about and who kind of discovered this different phenomenon. Okay, and it's kind of silly, but okay, we said that free-falling objects still have constant acceleration, and the acceleration that they experience is due to gravity, due to the gravitational force pulling objects down. Okay, good morning, Cameron. So the acceleration due to gravity is negative 9.8 meters per second squared. Thank you, ma'am. And that number is a constant. This is one we will have to know all the time. Okay, so you maybe highlight that, circle that, whatever you need to do in your notes, because that is a really, really, really important number, and it's one we're going to use a lot, okay? That acceleration is going to be for all vertical motion. Okay, let me say that again. Anytime we have a vertical motion, our acceleration will be negative 9.8. It will not be given to us in the problem. It won't be spelled out specifically, right? When we see objects that are moving in the vertical direction, we have to know that our acceleration in that kinematics equation is going to be negative 9.8 meters per second squared. Okay, do we feel okay with that? Okay, why is it negative? Think about what's gravity do. It pulls us down, right? So that negative has to deal with the fact that it's going in the downward direction. Okay? Okay. So we said that objects in free fall have constant acceleration in the y direction. When I say y, what's that mean? Vertical, right? So x and y, we need to know the difference between those. Y is the vertical direction. We said it has constant acceleration, but what do we know the acceleration is going to be? Negative 9.8, right? Negative 9.8. So I'm going to give you a second. If you would like to, you could rewrite your equations with the y variables instead of the x. Okay, you're welcome to do that. You don't have to, but you could. And so what I mean when I say that is the first equation is not going to change, right? Velocity final equals velocity initial plus a times t. But the second one, instead of having x final, we would have y final equals y initial plus plus v I t plus 1/2 a t squared, right? And then for our last one, we would have vf squared equals vi squared plus 2a y final minus y initial. So you don't have to rewrite these if you don't want to, but you can if that makes you more comfortable. The only thing that really changed is that we're not looking at horizontal displacement anymore, right? For x, we're looking at vertical displacement. And so that's really the only change that we see. Okay, not much else is changing. What's going to be the value for a in all of these equations? Negative 9.8. Okay, all of those are going to be negative 9.8. Now, I want to point out one more thing here. Sometimes when you see acceleration due to gravity, instead of an A, you might see a lowercase g for gravity, right? The acceleration due to gravity. You might see it as a g. So if it makes you more comfortable even, you could change these to g to remind yourself that it's going to be the acceleration due to gravity there. So you could do that if you want. You don't have to. Again, it's totally your choice about what you feel comfortable with. The more often we use these equations, the more comfortable you'll get with them. But if you wanted to put in a g there for acceleration, you can, because it is the acceleration due to gravity. Okay? Any questions so far? Okay. So let's go ahead and try one. Suppose that a ball is dropped from a tower that's 70 meters high. How far will it have fallen after 1 second, 2 seconds, and 3 seconds? So this problem asks us to solve for how far it's fallen at 3 different intervals. So this problem will require us to do an equation 3 different times. We cannot solve this in one stop. We have to do it 3 times, essentially. But let's get it set up and get an idea of what we're solving for and what that's going to look like, and then we'll go through what has to be done from there. Okay, so I want to just make a real rudimentary motion diagram here. Okay, it says that I've got an object on a tower that's 70 meters high. Okay, so I'm going to just draw a little cliff here, a little tower that has a height of 70 meters, right? Here's my ball on the top of it, and it's going to fall downward. Right? That's as complex as your motion diagram needs to get. I'm going to kind of encourage you to go ahead and draw a motion diagram, just a little one, with your problem so you have an idea of what the motion looks like and what it's supposed to look like. But it can be very simple, just like this, okay? Here's what I want you to understand when we do these problems. We talked about this a little bit at the beginning, but I want to refresh us a little bit. I always like to choose my origin, right? Where my object is starting at. So if I was going to be on a coordinate plane, I would draw my origin right there, right? Because that's where my object is starting from. And by putting my origin there, that allows me to basically say that my initial displacement is 0, right? By putting my origin at the top instead of at the ground, right? If we put our origin at the ground, our initial displacement would be 70. But I don't like that. I like my initial displacement to be 0. Does that kind of make sense? So instead of putting it at the ground, I'm going to put my origin always where my motion starts from. Now, I want you to think about this for just a second. Forget this part of the question. If we were trying to solve for how long it takes to fall to the ground, my final displacement would be negative 70. Don't write this down because that's not what we're doing on this problem, but I just want you to think about this for just a second. If the problem asked me, how long will it take to reach the ground? That means my ball would end up 70 meters below where it started. That's why we have a negative 70 in there. Does that make sense? If that were going to be what I was going to solve for, but it's not. So I wanted you to just see that first. But let's go ahead and examine what we are solving for, okay? It asks us, how far will it have fallen? So how far is it falling after 1 second, 2 seconds, 3 seconds? That means y final is really my question mark. So I'm not even going to use the 70 meters to help me solve my problem. I want to figure out how far has it fallen in that time. So the other information it gave me is that it's fallen for 1 second. Right, I'm going to do that one first. Now, the problem also gives me one other context clue. That's not a number. Do you have an idea what it might be? So what do you think it means that it's dropped? What variable does that refer to us? When I drop an object for just a second, that object stays at rest, right? Until gravity can start working on it to pull it down, it stays at rest. So the instant it leaves my hand, it's stopped, and then it starts to fall. So when an object is dropped, that tells me my initial velocity is 0, okay? If I would have said the rock was thrown, the ball was, thrown, projected, kicked, something like that, we would have a different initial velocity. But a dropped object always has an initial velocity of 0. So that might be another little extra note you put up here in your notes. Dropped objects have a VI equal to 0. right? That might be another little side note you put in there, that when we have an object that is dropped, it's going to have an initial velocity of 0. Okay, are we comfortable with that? Okay, so I think now this is all the information that we've been given. We've got one more variable that we can write down that's not in the problem. My acceleration is negative 9.8. It's never going to be given to you as a number in the problem. It's something you're going to have to know. Okay, as a vertical problem, that's what we have to know. So let's start examining now our equations and try to figure out which one can we use. Which equation could we use to help me solve for y final? The only two equations that have displacement in them are the second or the third. Right? And I don't have final velocity, so I cannot use the third equation. Right? It has to be the second. Would we agree with that? Okay, so let's go ahead and use the second equation. Y final equals y initial plus VIT plus 1/2 AT squared. All right, now I'm going to go ahead and put my numbers in for that. So my final displacement is what I'm solving for. My initial displacement is 0. My initial velocity is also 0, right? So that makes my equation pretty simple. 1/2 negative 9.8. And I have a time of 1 second. Okay, and so that gives me a y final equal to negative 4.9 meters. I know that why did my displacement come out to negative? It's below where it started. That's what you need to be thinking about. If my displacement is negative, it is below where it started. And so if my cliff has a height of 70 meters, after 1 second, I'm probably only about there, right? I've probably only fallen about that far, right? So this would be after 1 second. I've only reached that place, okay? Let's go ahead and try now to solve for it after 2 seconds. Can I use the exact same equation? Yeah, except my time now is not 1 second, it's 2 seconds. So I'm going to plug them in my equation here. Would we expect our displacement to just double? I guess we'll see. Okay, so instead of 1 squared, we're going to have 2 squared. About negative 19.6. So it didn't just double, right? Because our time is not just time, it's time squared, right? So because our time doubled, our displacement quadrupled, right? It's going to have that different effect. Okay, now I want to look at one thing here. Something we need to note is that the 19.6 meters is not from here 19.6 meters. It's still from the top, right? It's not like we went... After 1 second, we traveled 19.6 meters there. No, 19.6 meters is still from us being dropped at the top. Does that kind of make sense? It's not that we fall 19.6 additional meters. It's that in total, we fall in 19.6 meters. So let's see here. That's 35. That means we're probably, I don't know, around here at 2 seconds. Okay? Right? If that total length is 70 meters, 19.6, I don't know, it puts me somewhere around there. I'm not sure exactly, but let's go ahead and solve our final one here at 3 seconds. We can still use the same equation, except our time is 3. Is that what we had? All right, now I want you to kind of look at this demonstration over here. This really shows us the whole phenomenon of acceleration, right? After 1 second, I've only covered that distance. After 2 seconds, my speed is increasing, right? With every second that goes by, my velocity is increasing by 9.8 meters per second. And so as time goes on, I'm covering a lot greater distance, right? With every second that goes by, I'm not only getting faster, but that also means I'm covering more distance. So this phenomenon of after 1 second, we only cover this much. After 2 seconds, we cover that much. After 3 seconds, we cover that much. You see how the amount of area that we cover with each second gets greater? That is acceleration, right? That gives us a good visual of what acceleration is. Okay, do we feel kind of comfortable with solving that vertically? Okay, let's try the next one. Okay. Did I skip one? No. Okay. Suppose the ball from the last problem is thrown downward with an initial velocity of 3 meters per second instead of being dropped. What would its position be after 2 seconds? Okay, do we see the difference in these problems? The first one we drop, second one we throw downward. So it's going to make a difference. So before we even do any math, what would you expect your displacement to be? Would you expect your displacement to be greater than 19.6 meters or less than 19.6 meters? Greater than, right? We're expecting it to fall farther because it starts out with a velocity, right? And then it will speed up from there. So let's go ahead and solve our problem here. This is really important right here. It's thrown downward with an initial velocity of 3 meters per second. So my VI is what? It is not just 3, it's -3 because it's being thrown downward, right? That's important. It's being thrown downward. Okay, all of the other variables from our problem can stay the same. So we can still use that same equation. YF equals Y initial plus VI times T plus 1/2 A T squared. Right? Our initial velocity was not 0 this time, so we got to make sure we pay attention and put our initial velocity times our time in right there. Okay? Then we go ahead and solve our problem. Which that is what we would expect, right? So we've fallen a greater distance after that, after being thrown downward. So do you see how important context clues are in the problems, right? In these word problems, we really got to pay attention to, like in the last one, dropped, this one downward, right? You've got to use those context clues to help us determine some things about our problem. All right, let's try this one. A person throws a ball upward into the air with an initial velocity of 15 meters per second. Calculate how high it goes.
Can we basically just use the same equation?
We're going to use the same kinematics equations. Yes, we've just got to figure out what variables go where. But yes, we're always going to use, for this chapter, we're using those 3 kinematics equations. Okay, and then calculate how long the ball is in the air until it reaches his hand again. So we've got 2 different things we're calculating here, which means we're going to do them in two separate equations, okay? So let me draw a little diagram over here on the side. All right, here's our guy. Here's the ball. He's going to throw it upward. All right, it's going to reach some point, then it's going to come downward again. We agree with that, right? When we throw an object up, it's got to come back down, okay? And so we're trying to figure out how high is it going to go, and then how long does it take in total to reach his hand again. So let's figure out, where would I set my origin here? On the ground? I'm going to set it where the ball is, right? So I'm going to count his hand, wherever his hand is, right? That's where the ball starts and is going to stop again. That's where I'm going to set the origin. I don't care how far his arm is off the ground, right? That's where I'm going to set, because I'm only concerned about the motion from when the ball leaves the hand to when it goes up and comes back down and reaches his hand again, right? I don't care about the ground or anything like that. The origin, I set the origin where the motion starts from. So you'll see me draw that little crosshair, right, to kind of indicate that's where my origin is. Does that make sense? I'm going to encourage you to do that as well. So he throws the ball upward with an initial velocity of 15 meters per second. So here's my initial velocity. And is my initial velocity going to be positive or negative? Positive, right? Because he's throwing it upward. So positive velocity. The first thing we're going to calculate is how high it goes. So what variable is that going to be? How high? That's measured in meters. So what variable? Displacement, or y final, right? Y final is going to be my question mark. How high is it going to go? I always know that y initial is equal to 0. What else do I always know for vertical problems? Acceleration equals negative 9.8. All right, and then there's one more piece of information we have to know for this problem. If I want to solve for y final, I either need to have my time or I need to have my final velocity, right? But I know right here, it wants me to find my time later, so I don't have that. But what do I know about the final velocity of my object when it reaches this height? It has to stop. Bingo, right? When object is thrown into the air at its peak height, do you know what I mean when I say peak height? The highest point, at its highest point, it has to stop. So at its peak height, its velocity final is 0. Okay, velocity final is 0. Now, we need to understand that we are only examining right now the first half of the motion, right? We are only concerned with the ball from the hand to the top. And that's it. We're not worried about the fall right now. We're just looking at from the hand to its peak height. That's the only part of the motion that we're examining. Does that kind of make sense? Okay, so let's go ahead and find an equation then that helps us solve that. If I know my velocity final is equal to 0. Okay, which one should I use? My first, second, or my third to help me find y final? I can't use my second because I don't have time. I think the third. Okay, so we're going to go velocity final squared equals velocity initial squared plus 2 times a times y final, right? And there's no y initial, right? We said it's 0, so we don't need to include that in there. All right, let's go ahead and solve our numbers then. So 15 squared all right, what's my algebra from here? Can I combine these two terms? Are those like terms that I can combine? No, they're not, right? This one has a y final attached to it, and this one does not. So I have to subtract this to the other side. Negative 225 equals negative 19.6 y final. Okay, does that seem reasonable? Number one, our displacement came out positive, which it should, right? We threw it upward in the air, it came out positive. We want that. And it's not like a crazy high, crazy low number. Okay, so that seems good, right? Okay, now to solve for the time, I'm going to show us first kind of a shortcut method of how to do this, okay? So what I want you to think about is that when the object goes upward, do you think it takes the same amount of time to go up as it does to come down? I think it does. Yeah, it's crazy, but it does, okay? Because as it goes upward, it's slowing down, right, until it reaches 0. And as it falls, it starts slow and it speeds back up. So if I throw it upward with 15, it's going to land at negative 15 meters per second, right? It's going to have that alternate velocity. So if we can calculate the amount of time it takes to reach its peak height, we can just multiply that time by 2. Okay, so let me say that again. If our motion is symmetrical, if it goes straight up and straight back down, we're able to calculate the amount of time it takes to get to its peak height and then multiply by 2. Okay, that's the simplest way for us to do this. So let's go ahead and do that. If I want to solve for time at its peak height, I can use this same information because at my peak height, my velocity final is 0. My acceleration is still negative 9.8 and my initial velocity is 15. So I can use that first equation. I can use the first equation, VF equals VI plus AT. And that gives me a time of 1.53 seconds. But is that the time interval for the entire motion? No, it is only the time it takes to reach peak height. So I have to multiply that by 2. So it's really, really important, that extra step. This makes it a lot simpler for us to solve for time. But it's really important that we don't forget that times 2 step, right? Because the only place that our final velocity can be 0 vertically is when it's at its highest point, right? When it gets back to his hand right here, the final velocity would not be 0, right? Because it would be moving downward at that time. Okay, so the only time our final velocity would be 0 is only at the halfway mark. And then we multiply that by 2.